Welcome to today's GATE video. I am Prabha, Associate Professor of EEE Department, S.A.E. Engineering College. Today I am going to take types and performance of three-phase induction motor. First we will see what is a three-phase induction motor. Three-phase induction motor. An induction motor works under the principle of electromagnetic induction. It consists of stator and rotor. Stator is a stationary part, rotor is a rotating part. First, we will give a three-phase supply to the stator. The stator, after getting a three-phase supply, it consists of three-phase winding. When a three-phase supply is given to a three-phase winding, a rotating magnetic field will be created. This rotating magnetic field in the stator will cut the rotor conductors and EMF will be induced. Since rotor circuit is a rotating part and it is a closed circuit, the EMF produced in the rotor will produce a current and flux in the rotor. To produce a torque, there will be interaction of more than one flux. So the rotating magnetic field and the flux produced in the rotor will produce a torque. After the production of torque, motor will ready to run. The motor will run in the direction as that of the flux direction. Okay. Next, a three-phase induction motor or a self-starting motor. It does not need any external means to start the motor. Since it is producing a rotating flux, so it can start by itself. Types of three-phase induction motor. It consists of two types. One is squirrel cage induction motor. One is slip ring induction motor. So squirrel cage induction motor and slip ring induction motor. First we will see about the squirrel cage induction motor. So the rotor will have a cage-like structure. It does not consist of winding. It looks like a cage-like structure. That's why it is called a squirrel cage induction motor. It is made up of copper or aluminum bars, and the end of the bars is connected by end rings. It is short circuited by end rings, so it is also called as a short circuited rotor. Since it is short circuited in construction itself, so we cannot add external resistance to control the torque. So it is a moderate starting torque motor because the external resistance cannot have an impact on changing the torque production. So the rotor bars are permanently shorted. So the rotor bars, it is also called as a short circuit rotor. It is not possible to add the external resistance. And then this is the diagram for the squirrel cage induction motor. So it looks like a cage-like structure and it consists of bars, aluminum bars, and this is called as end ring. I already told that the end of the bars are connected through the end rings. This is called end ring, and these are the laminations. Why we are providing laminations? To reduce the eddy current loss. Eddy current loss can be reduced by using laminations. Next type of this induction motor is slip ring. It is also called as wound rotor induction machine. Slip ring induction motor is also called as wound rotor, and it consists of lamination on the outer periphery, and this rotor will have a winding. It consists of three-phase winding and it is connected to the slip rings. Slip ring is mainly used to connect the stationary circuit to the rotating part. It is same and then the number of rotor winding is same as the number of poles. That is very important. The number of winding should be equal to the number of poles of the stator winding. It can be connected either as star or delta. We can connect slip ring induction motor in star connection or delta connection. So the external resistance will be added in the slip ring. When for the squirrel cage we cannot add the external resistance because since it is short circuited in construction, but we can add external resistance in the slip ring induction motor. So the starting torque can be increased. That is, you can get high starting torque and the starting current can be limited in the starting time. So we can improve the starting torque. So it is used in the applications wherever the high starting torque is needed. So external resistance is added in the only the starting purpose, and in the running condition the external resistance can be removed from the circuit to improve the running current. This is the diagram for the slip ring induction motor. So the rotor winding is connected in star. This is star connected winding, and this portion is called as shaft, and this 3 is for slip ring for each winding R, Y and B, and it is connected through the rheostat, and the rheostat is connected to the slip ring. I already told that slip ring is used to connect the stationary circuit with the rotating circuit. Since it is a rotor, this is a rotating circuit, and rheostat cannot rotate, it is a stationary circuit. Through slip rings we can connect the stationary circuit to the rotating circuit. Using this rheostat we can limit the starting current, and the starting torque can be improved. So this is the torque slip characteristics, torque versus slip. So first, when you add the resistance, the maximum torque can be maintained constant. So additional resistance cannot have an impact on the maximum torque. Only the resistance will change the starting torque only. The maximum torque cannot be affected by the resistance when you increase the resistance. So this is the torque slip characteristics. This is called the starting torque. At the starting torque, the slip value will be equal to 1. For an induction motor, the slip range is 0 to 1. So when slip is equal to 1, then the starting torque, this starting torque will be here, and you will have a maximum torque, and this maintain constant for each adding the resistance. So R23 is greater than R22. So when we add the resistance, then the characteristics will come like this. So what is a slip? First, slip is the difference between synchronous speed and the actual speed of the motor. So the synchronous speed is Ns is equal to 120 F by P. The synchronous speed is produced in the stator, and the rotor speed, the difference between synchronous speed and the rotor speed is called as a slip. Slip will have a great impact on the torque developed by the motor. So it is acts as a key factor in determining the torque. In 3-phase induction motor, the maximum torque occurs when the resistance is equal to the rotor reactance. So for obtaining the maximum torque, R2 will be equal to X2. When these two values are equal, then we can get the maximum torque. So when slip S is equal to R2 divided by X2, the torque will be maximum, and this slip is called maximum slip. So this is the condition, S equal to R2 by X2, and ratio of rotor resistance to rotor reactance. R2 is rotor resistance, X2 is rotor resistance. Rotor reactance, X2 is rotor reactance, R2 is rotor resistance. At the starting condition, when slip is equal to 1, the maximum torque occur. Therefore, the condition will be changed to, when you substitute S equal to 1, R2 will be equal to X2. Next one is losses and efficiency. This is the block for the losses, for various losses. First we are giving the input power. The formula is, since it is a 3-phase supply, through 3 VL IL cos phi, and then stator copper loss. There will be a stator copper loss, core loss. Core loss is a constant loss, copper loss is a variable loss, and there is a air gap power here, and in the rotor we will have rotor copper loss, and mechanical losses will be present since it is a rotational motor. So rotating machine, so there will be a mechanical losses, friction and windage loss, and the last one is stay losses. It is a miscellaneous losses. After that we will get the output power. So first we will discuss about what are the losses. First, it is categorized into 2 types. One is constant loss and variable loss. Constant loss consists of core loss and mechanical loss, because core loss does not depends upon the load. Irrespective of the load, the core loss cannot vary. So it is maintained constant. Based on the construction only, the core loss will be decided. So core loss and mechanical losses is a fixed loss, and copper loss is called as a variable loss, because with respect to load, the current will be vary, therefore the copper loss will get changed. So this is the description for the iron or core loss. Iron or core loss, so it is a constant loss. It is again classified into 2 types. One is eddy current loss, other one is hysteresis loss. Eddy current loss, the current flowing in the core is called as eddy current. To reduce that eddy current, we are providing laminations to reduce the eddy current loss, and hysteresis loss can be reduced by having the core material with silicon steel. Next to mechanical losses, since there is a moving parts, so the mechanical losses will be present, windage and frictional losses. Next to copper loss. Copper loss, these losses are depends upon the resistance and the current. So based on the resistance, the current will be through the winding will be vary with respect to the load. When you increase the load, the current will get increases. Therefore, the load current increases, the losses will be increased. First we will see next the problem. First one will be a 3-phase 50 hertz 4-pole induction motor which is running at no load condition with a slip of 1%. So full load the slip increases to 5%. No load the slip is 1%. When you apply the load the slip increases to 5%. We have to calculate the speed regulation. So first given data given is frequency equal to 50 hertz, pole P equal to 4 and no load slip is 1%, full load slip is 5%. So speed regulation can be calculated. So the formula for finding out the speed regulation is no load speed minus full load speed by full load speed into 100. So first we will calculate the synchronous speed. The formula to find out synchronous speed is 120 F by P. So 120 into substitute the values for frequency and poles. So we getting NS is equal to 1500 RPM. Next we have to find out the rotor no load speed. N denotes no load, R denotes rotor. So the formula is NS into 1 minus SNL. NL is no load slip. Then substitute the values. NS just we got 1500 RPM, 1 minus and 1% is converted into decimal, we are getting 0.01 and the rotor no load speed will be 1485 RPM. Next we have to find out rotor full load speed. So the formula is again the same formula, but instead of using no load slip value, we have to use full load slip value. So 1500 into 1 minus 0.05, we are getting this value. The 5% is converted into decimal, so 1425 RPM. When we substitute the values of 1485 minus 1425 divided by the full load speed value, we are getting, when you multiply with 100, we are getting 4.21%. This is the answer for finding out the speed regulation. Next problem is we are having number of poles is 8 and frequency is 50 in slip ring induction motor which will have a rotor resistance 0.08 ohms and speed will be 650 RPM. The speed is given at maximum torque is 650 RPM. The additional resistance value should be calculated. We have to round off that to 2 decimal places. In the problem it is given neglect the magnetizing current, stator leakage impedance. So the equivalent circuit parameters referred to stator should also be considered. So this is the graph we are taken. So for R2 we are having the slip value here and this is for when we add the external resistance. This is the graph we are getting. First write the given values. P equal to 8, F is equal to 50 Hertz and rotor resistance R2 is given in the problem itself and speed is also mentioned in the problem. First step we have to find out the synchronous speed. Ns equal to 120 F by P. After substituting the values we are getting Ns equal to 750 RPM. Next we have to calculate speed corresponding to maximum torque and then so Sm equal to Ns minus Nr by Ns. So Sm equal to 750, Ns is 750 minus Nr is given 650 divided by 750 equal to the slip value is 0.133. Next we have to calculate rotor resistance already is given in the problem. So R2 is 0.08 ohms. Already we have discussed this formula that Sm slip at maximum torque is equal to R2 by X2. So now the R2 value is given. So we have to add external resistance because in the problem we have to calculate the additional resistance value only. So in the same formula I am adding the external resistance here. So R2 plus R external divided by X2. So keep this equation as 2. From these two equations we are having so R2 by Sm. Bring this Sm here and X2 here. Left hand side is equal. So that there X2 equal to R2 by Sm. Here X2 equal to R2 by Rx by Sm. So when you compare these two equations we are having this formula. So after substituting the values of R2, SM, everything, we are getting the external resistance value is 0.52 ohms. So for this problem, the correct answer is 0.52 ohms. The third problem is the power input is given as 40 kilowatts and the voltage is given 500 volts, frequency, poles, 3-phase induction motor, speed is also given 975 rpm, and frictional and windage losses is given as 2.025 kilowatts, stator losses are 1 kilowatt, efficiency should be calculated. So first given values will be first input power, voltage, frequency, poles, and the speed is rotor speed because it is given as running at 975 rpm, so that should be considered as rotor speed, and stator losses is given, convert into watts, and friction and windage loss, convert this also into watts. So first step is to find out air gap power. PG equal to input power minus stator loss. Input power is given as 40 kilowatts. Converting 40 kilowatts into watts, 40,000. Stator losses is 1000. Subtract when you get 39,000 watts. And rotor copper loss will be, copper loss is equal to S into PG. We have to find out the copper loss by using the formula slip into air gap power. So by using this formula, I am getting the value for copper loss equal to S into PG. First I am going to find out the PM also. PM is a mechanical power developed. So PG minus S into PG. PG is the air gap power minus slip into PG. This is nothing but your copper loss. So when you take PG as common, we will get PM equal to 1 minus S into PG. So after using the formula for synchronous speed, I am getting 1000 RPM. Using that 1000 RPM, slip can be calculated by the formula NS minus NR by NS. NS is synchronous speed, NR is rotor speed. In the previous slide, I have calculated NS is 1000. So 1000 minus 975 by 1000. So slip value is 0.025 value. So next we have to substitute the slip value in the mechanical power developed. In the previous slide, I told that PM is equal to 1 minus S into PG. So 1 minus, we got the slip value here 0.025 into PG is 39,000. So we are obtaining this result. Then find out the shaft power. Shaft power is the power taken at the shaft, that is at the end of the motor, and through the shaft power, PM is minus friction and windage loss. Shaft power can be calculated by the formula mechanical power developed minus frictional and windage loss. So just now we got 380.25 watts. Subtract this with friction and windage loss, we are getting this answer. Next we have to find out the efficiency. So efficiency is output power by input power. Output power is nothing but the shaft power. So shaft power by input power. So 36,000 by 40,000 into 100. The efficiency value is 90%. Next, fourth problem. The frequency of stator and rotor current is given for a 8-pole induction motor. The frequency of stator is 40 Hz and rotor is 1 Hz. The motor speed is, we have to calculate and round off to nearest integer. It is given in the problem like this. So pole is equal to 8 and rotor frequency is 1 Hz and stator frequency is 40 Hz, and rotor current frequency formula is FR equal to slip into Fs. So from this we can find out slip. Slip is equal to Fr by Fs. So 1 by 40, we are getting the slip value is 0.025. Next step, we have to calculate the synchronous speed. Already we know the formula for synchronous speed, 120 F by P. Here we have to use the frequency as stator frequency, 120 into supply frequency, 120 into 40 divided by 8, so 600 RPM. Using the synchronous speed and the slip value, we have to find out the rotor speed, 600 into 1 minus 0.025. So we are getting the rotor speed as 585 RPM. So the last rotor speed answer is 585 RPM. In the next video, I will continue the power system subject. Thank you.